Hello everyone, my presentation title is Restructured Colonial Vulnerability Detection based on Function Semantic Reserving and Reiteration Screen. My name is Jiang Weipeng, and I have graduated from DK Laboratory of Information Security. First is the introduction. Recently, there exists great number of open source projects, such as the most famous open source platform, GitHub. Till the end of 2018, there are more than 100 million repositories on GitHub. These repositories covering almost all the programming languages, ranging from C, C++, Python to JS. Most of the common functions can be found on all kinds of open source platforms. Due to the large quality, diverse functions, and easy access, open source projects saved a lot of working for common developers. For example, if a developer wants to develop his own system, maybe he will search the GitHub to find a similar repository and clone it. Then he just needs to customize the cloned code to meet his requirement. Frankly, employing code clones did bring convenience, which therefore contribute to the volume of code clones. However, since the code clones are almost directly copied from the original system, they would also introduce the existing vulnerabilities into target projects. Then the vulnerabilities would do great harm to the target system, including being exploited to conduct denial of service or execution of attribute code remotely. As the developers who copy codes are not likely to patch the cloned code timely, the system will be at risk for a long time. Then here's the question: how can we deal with the vulnerabilities brought by the code clones? A practical way is to detect the target project in advance to lower the risk. Some researchers propose that we could use clone detection to detect the vulnerability, which is also the content of this paper. Then I will introduce some common concepts used in our paper. The curtain clone detection is mainly divided into 4 levels, namely exact clone, renamed clone, restructured clone, and semantic clone. The specific examples are shown in the figure. Exact clone will copy without any changes. Renamed clone will modify the identifier, variable name, or function name. Restructured clone will add or delete some lines of code, and semantic clone just has the same semantic but different grammars. Also, the granularity of clone detection is divided into 5 granularities, including token, line, function, file, and program. The research on detection of clones mainly focus on the first 2 types, but we found that the third type will also introduce vulnerabilities. But the curtain tools cannot effectively detect them. As for the 4th level, we think that the semantic clone will destroy the original vulnerability in most cases, so the type 4 clone was not considered in this study. Because that type 3 clones have code additions and deletions, we need to use lines as the granularity for clone detection so that the impact of additions or deletions can be avoided. We propose to use program slicing to obtain discontinuous code fragment representation vulnerabilities, which can achieve the detection of type 3 restricted clones. Program slicing is a technique for extracting code snips from a target program, which would affect specific data. The specific data is called slicing criterion in program slicing. Next, I will introduce the overall structure of our method. We propose a restructured colonial vulnerability detector ++, which is also called RCVD++. It uses code patches and program slicing to obtain code fragments related to vulnerabilities, abstract the code fragments into precise fingerprint with semantic reserving function abstraction, and retroactively screen the detection result to reduce false alarm. There are two stages in RCVD++ as shown in Figure 1. Fingerprint database generation and colonial vulnerability detection. The first stage, establishment of fingerprint databases. It utilizes two granularities to generate a fingerprint, including line and function. Type 3 fingerprints are generated by the granularity of line, and the official patch fingerprints are generated by the granularity of function, and are linked to corresponding Type 3 fingerprints. Type 1 and Type 2 fingerprints are generated by the granularity of functions. As shown in Figure 2, the vulnerable code will be abstracted in the granularity of line and function. The first substep in stage 1 is to pre-processing. In order to retrieve the information about vulnerabilities more conveniently, the codes are corrupted from open source projects hosted on GitHub, which also makes it easier to get patch information from the commit history. To extract vulnerability-related code, we leverage various information embedded within the commit history. The first substep is program slicing based on patches. And Table 1 lists an example of program slicing. We take the deleted free A statement in the patch as slicing criterion to get forward slice and backward slice. These sliced codes contain the key statements that variable A is freed twice, and there are no statements unrelated to vulnerabilities, which demonstrates that patches-based program slicing can effectively extract the critical code lines related to the vulnerability. Next substep is function abstraction towards semantic reserving. The first column in Table 2 shows abstracted function names, while the second one shows the actual function ones, clearly preserving more semantics. Substep 4 is fingerprint generation. Obviously, two different lines of code need to be completely different after conversion, and the cost should be as little as possible. Since MD5 hash algorithm is naturally lightweight and strict enough for the requirement it is employed in this process, we calculate the MD5 for each line of code to generate the fingerprint. The second stage is colonial vulnerability detection. In this stage, the target code will be transformed into a fingerprint and then compared with different fingerprints to determine whether it is vulnerable. The entire process is shown in Figure 3. RCVD++ will first pre-process the code to generate a fingerprint at function granularity, and then use the Type 1 and Type 2 fingerprint database to perform fingerprint matching. If the match is successful, a detection result will be generated directly. Otherwise, the Type 3 clone detection will be performed. If the target code matches the Type 3 fingerprint successfully, RCVD++ will trace Type 3 fingerprint back to figure out whether the code is patched and outputs the detection result. The sub-step 1 in stage 2 is hash lookup. We need to look up all the hash values corresponding to the length of target code string after abstraction, and then find out whether there is a same hash as the target code in the hash values with the similar. The sub-step 2 is greedy-based fingerprint matching algorithm. As shown in algorithm 1, the C is the target code and F is the fingerprint. We will compare the target code with fingerprint one by one and line by line to figure out whether there is a fingerprint that matches the target code. And it obviously that it has a linear relationship with the length of code and the number of fingerprints. Next substep is reiteration screen. This process is based on the official patch fingerprints generated at the function granularity. For each Type 3 fingerprint, a patched version is avoidable. Then we will link the official patch fingerprint with the corresponding Type 3 fingerprint. Figure 4 shows the diagram of the linked Type 3 fingerprint and official patch fingerprint data structure used in the reiteration screen process. Next, I will introduce the experiments conducted in our paper. First is the setup, and we run our experiments on a machine with CentOS. About the metrics, we optimize the common accepted metrics including false positive rate, false negative rate, accuracy, precision, and F1 score. The first experiment is compared with other cloning vulnerability detectors, including RCVD and Redebug. The configuration is shown in Table 5. For RCVD++ and RCVD, we're using NVD and the Linux kernel for fingerprint generating. For Redebug, we utilize the configuration in their paper with n equal to 4 and c equal to 10. The detection result is shown in Table 6 and Table 7. It can be seen from the detection results that the F1 score of RCVD++ have reached the 96.67% and 93.39%, which is significantly better than other tools. RCVD++ has a higher accuracy rate and precision, which means it can find more vulnerabilities without introducing too many false positives, reducing the cost of manual review. At the same time, RCVD++ has a lower false negative rate, which proves the effectiveness of the reiteration screen method proposed in our paper. Then we further compare the RCVD++ and RCVD in the NVD clone dataset. And we set up 4 different experiments for comparison, each method proposed in this paper. Every experiment add a optimized method. As shown, semantic reserving abstraction reduces the number of positive by 2. And the type 1, type 2 fingerprint significantly improves the number of true positive by 354. About a reiteration screen, it could effectively identify the patched code, resulting in a decline in the number of false positives by 56. The results fully prove that RCVD++ greatly improves the effectiveness of RCVD in detecting cloning vulnerabilities. Then we compare our tool with other clone detectors, including Deckard and CloneWorks. These two tools is mainly designed for clone detectors rather than detecting vulnerabilities. As shown in the table 10, RCVD++ still has higher precision and accuracy, and also the FE score. Next, I will introduce some related works. Firstly, about clone detection, the earlier clone detecting tool is CCFinder, proposed in 2002. It measured the similarity of a sequence of tokens by a suffix tree algorithm. Social CC uses a bag of tokens strategy to manage minor to specific changes in clones. However, they are mainly designed to measure similarity and is not suitable for vulnerable code clone detection. Then, Lee proposed the CP Miner, the first vulnerable code clone detector. As we can see, there are a lot of related works that detect the vulnerable code clones. They utilize all kinds of properties of programs such as AST, PDG. Then use different algorithms including Bloom filter, cluster, to measure the similarity of vulnerable code and target code. In addition, there are detection methods based on machine learning. Lean extract the features from AST and use LSTM to learn the representation. WLDPacker is the first to use deep learning for detecting. Through the introduction above, we can find that the current detection of clone code vulnerabilities can be divided into two categories. The first type is to detect by measuring the similarity between the target code and the vulnerable code. And the second type is an artificial intelligence-based detection method. It actually contains two phases, except that the first phase uses machine learning to train the network, and the second phase uses the network to detect a vulnerability. And WLDPacker is one of the most representative examples. Finally is the conclusion. In this paper, we propose our detection method RCVD++. So far, the work can also be extended in multiple directions. Dynamic analysis could be used to obtain more accurate vulnerable codes, and optimize the abstraction method and identify more functions to return more semantic information. Third, combine machine learning algorithms to further improve the effectiveness of our method. That's all. Thank you.